We're going to start with Unit 12, Part 2. So we use this as well as 13.1 to kind of describe what we're covering, which is solving trig equations. So on our first slide, we're going to be taking a look at various different types of problems, but most importantly, at the very bottom, you're going to see what we will be using to figure out these different equations. Now, you need to know your unit table or your unit circle, one or the other. So let's first begin with number 4. Here we have arcsine. With arcsine, remember, we are looking at the inverse sine of 1/2. So this is extremely easy to use once you know your table. You're going to go ahead, take a look at the sine function, and we're going to look to see where it is 1/2. In this case, that occurs with pi over 6. So our answer here would be pi over 6. Let's go ahead and take a look at example 9. Now we're looking at the inverse sine, which is the same as arcsine, but of a negative number. Whenever that occurs, you know that you're going to be keeping that negative number. And we know that because, remember, when we were dealing with the sine, cosine, and tangent families for the even-odd identities, we realized that every single time that it was either tangent or sine, or cotangent and cosecant, they ended up being negative. It stayed negative. But for cosine, it turns positive. So here, we're going to begin with the sine of square root of 3 over 2, which we can see is pi over 3. Number 14, we have tangent or inverse tangent of a negative square root of 3. In this case, our answer is going to remain negative. With tangent being the square root of 3, we're going to be looking at a negative pi over 3. Inverse cosine of 1 with a positive 1/2 will be a positive pi over 6. Arcsine of a negative 1. Now, in this case, what I generally suggest is to go ahead and rewrite this as negative sine inverse of 1. This will help you find it a little bit easier once you are able to use that even-odd identity and bring it out to the front. In this case, your answer would be a negative, because once again, it's sine, and it's a negative number, pi over 2. Let's take a look at number 15. With 15, we're looking at the inverse cosine of a negative square root of 3 over 2. First thing would be, it would be negative. And we're going to take a look to see where we have that square root of 3 over 2, which is going to be at the pi over 6 mark. Number 6, arcsine of negative 1/2. Once again, we have a negative number, which means it's going to remain negative. 1/2 for sine is going to give us pi over 6. Arc cosine of negative 1/2. Now in this case, if we pay attention, you will realize that with cosine, remember, it remains positive, even though our number is negative. So that means that once we are here, this is going to remain as a positive of 1/2. So in that case, we find cosine, we find out where it's going to be 1/2, which in this case is going to be pi over 3. Number 16, we're looking at the arc cosine of 4. Now, with that, we already can tell that with 4, it is outside of the unit circle. So the fact that it's outside the unit circle, we can go ahead, place that over 1, and we can draw out where we are looking at. This would be in quadrant 1, because if you notice, 4 over 1, both are positive. We would go 4 to the right, and our hypotenuse would be 1. In this case, it would be not applicable because we are outside of the unit circle. Number 7, we're looking at the inverse cosine of 0, which would be pi over 2. arctangent for number 8 of 1. Notice 1 would be pi over 4. It is a positive number, which means it remains as a positive 4. We're going to go ahead and take a look at number 12. For number 12, we have the inverse sine of a negative square root of 2 over 2. For that problem, we are going to remain with a negative number. Square root of 2 over 2 is a pi over 4. Tangent of square root of 3 over 3, it's remaining positive. We know that we're going to be working at pi over 6. Number 8, we have arctangent of 1, which we already solved, and was pi over 4. Number 13, arc cosine, or the inverse cosine of a negative number. Remember, it's going to turn positive. Square root of 2 over 2 is going to give us pi over 4. Last one would be sine of 0. In this case, keep in mind, whenever we have the sine of 0, the only place where we have that occur would be at 0. Keep in mind, 1, 0, 0, negative 1, 1, 0, and negative 1, 0. Here we're taking a look at slide 3. In slide 3, we're going to review the periods for each one of our trig functions. So for sine, we're going to be looking at 2 pi, cosine would be 2 pi, and tangent would be pi. Now, this is extremely important because it would be affecting the general form of your equation. So we're going to start off with first understanding our sample problem, which is sine of x is equal to 1/2. Now, the same way that we did this problem before, we're going to repeat the problem. Notice we have a sine, and it's of a positive number. So we know that our radian is going to be a positive number. So we're going to end up at x equaling pi over 6. Just for you to have a better understanding of it, that would be 30 degrees. Now, we generally use radians to describe all of our numbers. We are not using degrees, but we're going to go over it here just to be able to make sure that you're having a full understanding of the values we're talking about. Now, as we take a look at pi over 6, we also have to realize that there are other areas where sine can be positive. In this case, when we complete our table of all students take calculus, notice we're going to see that in this case, quadrant 1 and quadrant 2 are both positive for sine. If this is pi over 6, we would have 5 pi over 6 be in quadrant 2. So we would go ahead, we would write down our other value for x. X is equal to 5 pi over 6, which is equal to 150 degrees. You could find other coterminals that can go further from that pi over 6 or the 5 pi over 6, but just keep in mind that we are going to be given a range to stay within as we go further and further into this section. Now, when we start working with the unit circle, it's going to become very important that we are using the general form. So the general form would be adding 2 pi k. Now, it can also be adding pi k. This will occur for sine and cosine, and this would occur for tangent. Once again, this is in reference to their periods, just like we had spoken about before. So for this problem that we're currently working on, which is the sine of x is equal to 1/2, we ended up getting x is equal to pi over 6, and we're going to add plus 2 pi k because of the pure fact that it is a sine equation. Our other answer would be x is equal to 5 pi over 6 plus 2 pi k. This is considered general form. Now, this is also going to be considered from the interval from 0 to 2 pi. Now, we're going to include the 0, but we're not going to include the 2 pi. Keep in mind, 2 pi is 360 degrees, which means that we would be going in a full circle. Once we've included 0, we would also be including that 360 of where it originally started. Let's go ahead and take a slide 4 and take a look at that. So some helpful facts for trig equations. The most important from this slide would be the two types of solutions. Here we have a general formula for all the solutions, or we have specific values that are given in between 0 to 2 pi. So depending on where it is that we are talking about, whether it is an exact value or whether it's a general formula, you should know how to complete both of these different types. It's also extremely important to know that the identities such as sine squared of x plus cosine squared of x is equal to 1 could also be used to substitute into an equation. Third key fact would be everything is written in radians. As we take a look at slide 5, we're going to take a look at the sample problem of cosine of 3x is equal to 1/2. As we're working this problem, the first thing to pay attention to would be the fact that we have a 3 in front of the x. Now, the most important part is to isolate the cosine and your theta. If there's a number attached to it, whether it's being multiplied by or divided by, you would be able to leave it there and solve for that specific problem. Now, in this case, we're going to initially look at just cosine and everything that we have with cosine of 1/2. Cosine of 1/2 is positive because it is going to turn positive, but the number itself is also positive. So where would we find 1/2? We would find it at pi over 3. With us being at pi over 3, we would set the 3x, or our theta, and whatever number is attached to it, equal to pi over 3, and we would find its other number. Keep in mind, all students take calculus. In this case, since we're working with cosine, we're going to be in the first quadrant and the fourth quadrant. Our first quadrant, we're going to be at pi over 3, which means that we would be at a 5 pi over 3 in the fourth quadrant. We set our equation of 3x equal to the pi over 3 and 5 pi over 3. Once we've written it in our general form, we're going to go ahead and divide all sides by 3. Now keep in mind, we are only working with an addition for these problems. Once we divide all sides by 3, notice pi over 3 divided by 3 is pi over 9, and 2k pi divided by 3 is 2k pi over 3. Now keep in mind, it does not matter whether you put 2k pi or 2 pi k. I generally suggest that you keep it as 2 pi k in order to know that and understand that the variable of k is a constant, and to also understand that 2 pi is the period that is being represented by cosine. The same thing would occur with sine, but in tangent, it would only be pi and then your k. As you take a look at the right-hand side, you can easily see that that side was also divided by 3. So 5 pi divided by 3, divided by 3 once again, would actually cause it to turn into 3 times 3, which is 9, so 5 pi over 9. We once again divide by 3 on the right side and end up with 2 pi k divided by 3. Let's take a look at slide 6. In slide 6, we begin to take a look at problems that are mainly isolating our trig function along with theta. And we begin to roll into around question 4, what happens when things are added in front of or behind our trig sine theta. Let's begin with number 2. So number 2, we have the tangent theta of -1. So the first thing to kind of understand is that all students take calculus. We realize that we're going to be working with quadrant 2 and quadrant 4. We know that because we're working with tangent, and our tangent in this case is going to be a -1. We're going to take a look at our table. Slide that into frame. Now, tangent of theta would be -1 in 2 locations. We're going to end up with that occurring at pi over 4 plus pi k, and theta would also be equal to 3 pi over 4 plus pi k. Remember, the pi k occurs because it is tangent. If it was sine or cosine, we would have 2 pi k. Let's go ahead and take a look at the tangent of the square root of 3 over 3. Once again, we lay out our all students take calculus. Because we're dealing with a positive number, we're going to be in the first quadrant and the third quadrant. Now, square root of 3 over 3 would leave us with pi over 6. So we have theta is equal to pi over 6 plus pi k. Our other theta would be 7 pi over 6 plus pi k. For number 4, we're now taking a look at what occurs when we have sine and when we have more than just the term by itself. So what occurs is we want to keep the sine pi by itself. So the first thing we're going to do is we're going to move over the 1, and we're going to get sine of theta equal to -1. The fact that we're working with a negative sign, remember, all students take calculus. In order for us to find negative spots, we would generally say, oh, it's going to fall into the third and fourth quadrant. But keep in mind, we are working with a number of 1. In this case, it does fall within the actual unit circle, but it falls outside of our table. So we go ahead and we take a look at where we would fall sine into 1. This would be 1, 0, -1, 0, 0, 1, 0, -1. This can only occur in one place, which is 3 pi over 2. We go ahead and write down that theta is equal to 3 pi over 2 plus 2 pi k. Let's go on to number 5. In number 5, taking a look at 2 cosine theta. Once again, we want to get the cosine theta by itself. So in this case, we're going to divide by 2 first. Cosine theta is equal to the square root of 3 over 2. Once we find its 2 locations, which in this case would be at pi over 6, we would set theta equal to pi over 6 plus 2 pi k. Now, we are also, keep in mind, if we're dealing with cosine, it would be positive in quadrants 1 and 4. Because of that, we are going to also take a look at where pi over 6 would occur in the 4th quadrant. That would mean that theta is equal to 11 pi over 6 plus 2 pi k. Let's go ahead and take a look at slide 7. In slide 7, we are now taking a look at the same type of problems. The only main difference would be that we are now finding more items outside of our trig function and our theta. There is an order to doing this, and you have to either add or subtract first, to move over to the right side. And then your step 2 would be to multiply or divide. So let's take a look at number 6. In this case, our first step is going to be to move the positive 2 to the right-hand side. We would have 3 square root of 2 cosine theta is equal to negative 3. We're going to divide by 3 square root of 2, which leaves us with cosine theta is equal to negative 3 over 3 square root of 2. This simplifies to negative 1 over square root of 2. Once it's rationalized, it would turn into a negative square root of 2 over 2. We're going to take a look at where we have a square root of 2 over 2 for cosine and figure where it would be within our graph. Now in this case, if we're looking for a negative number and we are working with cosine, we would have to go ahead and the placement would be in quadrants 2 and 3. We go to negative square root of 2 over 2, and this would be a pi over that would be pi over 4, which means that we would go ahead and write our equations out first. So if we have it in the first quadrant, this would be pi over 4. We then have to move it into the second and third quadrants. Our second quadrant would be 3 pi over 4 plus 2 pi k, and theta would be 5 pi over 4 plus 2 pi k. Let's take a look at number 7. Number 7 is very similar. Keep in mind, because of the fact that the 2 is attached to the theta, we're going to leave that in this case. And what's going to happen is that we are going to go ahead and just work the problem as regular. Because we are working with tangent and we are working with a positive tangent, remember, all students take calculus, we would be in the first and fourth quadrant. In this case, we're looking at pi over 3. So theta over 2 is equal to pi over 3 plus pi k, and theta over 2 is equal to 4 pi over 3 plus pi k. Now, we still have the 2 attached to the theta over 2. So what's going to occur is that we're going to multiply everything by 2. That means both sides of it are equal sign. That would cancel off the 2 underneath our theta is equal to 2 pi over 3 plus 2 pi k, and theta is equal to 8 pi over 3 plus 2 pi k. Let's go ahead and take a look at number 8. In this case, it's the same scenario as in number 7. The only difference is that rather than having theta divided by 2, we have 2 theta. We're going to go ahead and find where cosine would be equal to 1/2. In this case, we know that all students take calculus, and we're looking for a positive number, which means first and fourth quadrant. Our 2 theta would be equal to pi over 3 plus 2 pi k, and 2 theta is equal to 5 pi over 3 plus 2 pi k. We're going to go ahead and isolate theta by, in this case, dividing by 2. So theta is equal to pi over 6 plus pi k, and theta is equal to 5 pi over 6 plus pi k. In example number 9, we have to isolate cosine and theta. Now in this case, we do have a square, which we will have to take care of, but we slowly start working on the outside first, which means the cosine squared theta is equal to 3 over 4. In order to isolate cosine and theta, we have to get the square root of both sides. This is going to give us cosine of theta is equal to square root of 3 over 4, which is equal to the square root of 3 over 2. Now, once we find the square root of 3 over 2, we're going to go ahead and keep in mind, because we're working with a square root, this would be a positive and negative in front of it. We're going to take a look for the square root of 3 over 2, which is going to give us, in this case, all 4 quadrants. So this means we would have theta is equal to pi over 6 plus 2 pi k. We would have theta is equal to 5 pi over 6 plus 2 pi k. We would have theta is equal to 7 pi over 6 plus 2 pi k. And final one would be theta equaling 11 pi over 6 plus 2 pi k. Question number 10. We are taking a look at a problem that is very similar to a polynomial. In this case, with a polynomial, the same thing that we would do usually, where we would go ahead and set the entire equation to 0, is the exact first step that we're going to take. We're going to move over the 1, so 2 sine squared x plus sine x minus 1 is equal to 0. And we're going to go ahead and factor out our 2 halves that equal 0. In this case, this is going to be 2 sine x, and we're going to have a plus 1 and minus 1. and sine x plus 1. The same way that we would factor, we're going to go ahead and set each one of these equal to 0. So 2 sine x minus 1 is equal to 0, and sine x plus 1 equals to 0. We're going to go ahead and solve each side. First would be add 1, so 2 sine x is equal to 1. Sine of x is equal to 1/2. In this case, we would then go ahead to the right side. Sine of x is equal to -1. In this case, we go ahead, determine that in order for us to end up exactly where we need to be, we would have x for sine equaling -1. Remember, this is 0, 1. This is 0, -1. 1, 0, -1, 0. In this case, this would be 3 pi over 2. So x is equal to 3 pi over 2 plus 2 pi k. On our other side, we have sine of x is equal to 1/2. So we go ahead, take a look at our table. The sine of 1/2 would give us pi over 6. So we have x is equal to pi over 6 plus 2 pi k. Let's go ahead and take a look at slide 8. In slide 8, the problem is done the exact same way. We're first going to isolate our cosine of 2 theta. We are being given the range of 0 to 2 pi. Now, this is extremely important because we will have to find exact values. So let's go ahead and work this problem out. We're first going to have 2 cosine of 2 theta is equal to 1. Cosine of 2 theta is equal to 1/2. Keep in mind, cosine would be positive in quadrants 1 and 4. We're going to get two values from this, and we're going to end up with 2 theta is equal to pi over 3 plus 2 pi k, and 2 theta is equal to 5 pi over 3 plus 2 pi k. We're going to divide both sides by 2, which in this case, theta would be equal to pi over 6 plus pi k, and theta is equal to 5 pi over 6 plus pi k. Now, in the case for pi, because we're looking for an exact value and we're solving, we're going to go ahead and set it equal to our original number of pi over 6, or 5 pi over 6. So we have theta is equal to pi over 6 plus 6 pi over 6 k. And we're going to do the same thing for our other problem. Theta is equal to 5 pi over 6 plus 6 pi over 6. In order to figure out what would fall between 0 and 2 pi, we're going to go ahead and set numbers equal for k. We're going to start off with k equaling 0. So if k equals 0 and we placed it into that first equation, 0 times 6 pi over 6 is 0. Our answer would be pi over 6. That's extremely important to determine, does it fall between 0 and 2 pi, just like our question had asked us. We're going to do the same thing for k is equal to 1. 1 times 6 pi over 6 is 6 pi over 6, plus pi over 6 is 7 pi over 6. Notice, once again, it falls in between 0 and 2 pi. We go ahead and try 2, and we continue working this until we fully run out of options because it does not fit within that domain. In this case, 2 times 6 is 12. Now keep in mind, with a denominator of 6, 2 pi would be 12 pi over 6. And keep in mind, 2 pi is not included when we are talking about the maximum number. So we would have to be at 11 pi over 6 or less than that in order for it to fall within. So the two answers that we have for this, one equation would be pi over 6 and 7 pi over 6. Let's complete the right-hand side. We'll start off with k equaling 0. That would give us 5 pi over 6. And k equals 1 would give us 11 pi. Over 6. Our final solution set for this problem would be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6.